Is reality just math? Look around you, what do you see? Perhaps a book, a tree, or the twinkling of distant stars. We perceive our world as a collection of physical objects and phenomena, governed by laws of nature. But what if I told you that everything you see, everything you touch, and even yourself, might be at the most fundamental level just math? This isn't as crazy as it sounds. For centuries, mathematicians and physicists have been awestruck by the uncanny ability of mathematics to describe our universe. From the elegant orbits of planets to the bizarre behavior of subatomic particles, mathematics seems to be the language that the universe understands. But what if it's more than just a language? What if the universe isn't just described by math but is math? This is the essence of the mathematical universe hypothesis, a mind-bending idea that has captivated physicists and philosophers alike. It suggests that our physical reality is not just based on mathematical principles, but is itself a mathematical structure. In other words, the universe is not just described by math, it is math. To grasp the mathematical universe hypothesis, we need to appreciate the profound relationship between mathematics and physics. Throughout history, mathematics has proven to be incredibly effective at describing the natural world. From Newton's laws of motion to Einstein's theory of relativity, our most successful physical theories are expressed in the language of mathematics. These mathematical equations don't just describe how things move or interact, they reveal deep underlying patterns and principles that govern the behavior of the universe. The more we explore the universe, the more we find that it seems to follow a set of elegant and often surprising mathematical rules. This remarkable effectiveness of mathematics has led some physicists to believe that it's more than just a tool for describing reality. It's the very fabric of reality itself. This idea that the universe is fundamentally mathematical challenges our conventional understanding of the cosmos and raises profound questions about the nature of existence. The traditional view of physics sees mathematics as a powerful tool for describing and predicting the behavior of the physical world. We observe the universe, formulate mathematical laws that seem to fit our observations, and then use these laws to make predictions about future events. However, the mathematical universe hypothesis takes this a step further. It proposes that the mathematical structures themselves are not just descriptions of reality, but are reality. In this view, the universe is not something separate from mathematics, but rather a manifestation of mathematics itself. This shift in perspective has profound implications. It suggests that the properties of the universe are not arbitrary, but stem directly from the underlying mathematical structure. The laws of physics, the fundamental constants, and even the initial conditions of the universe would all be consequences of this fundamental mathematical reality. The mathematical universe hypothesis, championed by cosmologist Max Tegmark, takes this idea to its ultimate conclusion. It posits that our physical universe is not just described by some mathematical structure, but it is a mathematical structure. Imagine, for instance, the set of all possible mathematical structures, a vast and diverse landscape of pure abstract mathematics. Within this landscape, according to the hypothesis, exists our universe, not as a separate entity, but as one specific mathematical structure among countless others. Every electron, every star, every galaxy, and even every thought we have is, at its core, a manifestation of this underlying mathematical architecture. This means that the universe is not just governed by mathematical laws, but is itself a mathematical entity. The laws of physics are not imposed on the universe from the outside, but emerge organically from its mathematical structure, just as the rules of arithmetic emerge from the structure of numbers. The idea of a reality underpinned by mathematics might seem radical, but it echoes an ancient philosophical concept, Plato's theory of forms. Plato argued that the physical world we perceive is just a shadow of a more fundamental realm of perfect, unchanging forms. These forms, such as the form of beauty or the form of justice, exist outside of space and time and represent the true essence of reality. While Plato didn't explicitly link his forms to mathematics, the MUH can be seen as a modern interpretation of his ideas. In this view, the mathematical structures play the role of Plato's forms, representing the eternal, unchanging blueprints from which our physical reality is derived. Just as the shadows in Plato's allegory represent imperfect reflections of the forms, our physical world, in the MUH, is a manifestation of a deeper, more fundamental mathematical reality. The MO, therefore, bridges a gap between ancient philosophy and modern cosmology, suggesting that the universe might be more than meets the eye, rooted in a realm of abstract, timeless mathematics. To truly grasp the MUH, we need to make a conceptual leap and imagine a reality that exists solely in the realm of mathematics. This is a realm devoid of familiar physical attributes like space, time, matter, and energy. Instead, it's a realm of pure, abstract structures, defined by mathematical relationships and equations. These structures, according to the MUH, are not just abstract concepts, they have an independent existence. They are the fundamental building blocks of reality, and our physical universe is just one particular manifestation of these structures. Think of it like this: a musical symphony is more than just the vibrations of instruments. It's a complex interplay of musical notes, rhythms, and harmonies, all governed by mathematical ratios and patterns. Similarly, our universe, in the MUH, is a grand symphony of mathematical structures, playing out their intricate dance in the theater of space-time. If our universe is indeed a mathematical structure, this raises the intriguing possibility that ours might not be the only one. Just as there are countless mathematical structures, there could be countless universes, each a unique manifestation of a different set of mathematical equations. This is the concept of a multiverse, a collection of universes existing alongside or within our own. These universes might have different physical laws, different dimensions, and even different types of matter and energy. Some might be hospitable to life, while others might be strange and inhospitable. The muck doesn't necessarily imply the existence of a multiverse, but it makes it a tantalizing possibility. If the universe is ultimately mathematical, then the existence of other mathematical universes seems not just plausible, but almost inevitable. A common question about the mathematical universe hypothesis is this: if our universe is just a mathematical structure, can we ever prove it? After all, we experience the universe through our senses, which are attuned to physical phenomena, not abstract mathematics. This is where the MUH faces its biggest challenge. While it offers an elegant and compelling explanation for the universe, it's not clear how we could definitively prove or disprove it through direct observation. However, even if we can't directly observe the underlying mathematical structure of the universe, we might be able to find evidence for it indirectly. For example, if the universe is truly mathematical, we might expect to find deep connections between seemingly unrelated physical phenomena, reflecting the underlying mathematical unity. If the MUH is true, it has profound implications for our understanding of reality and our place within it. It suggests that the universe is not a random collection of particles and forces, but a deeply ordered and interconnected entity, governed by elegant mathematical principles. It also challenges our anthropocentric view of the cosmos. If the universe is fundamentally mathematical, then life, consciousness, and even our own existence might be seen as emergent properties of this underlying mathematical reality. This doesn't diminish the significance of life or consciousness, but it places them within a grander, more awe-inspiring context. We are not just insignificant specks in a vast and indifferent universe. We are integral parts of a magnificent mathematical tapestry woven from the very fabric of existence. One of the most appealing aspects of the MUH is its elegance and simplicity. It offers a unified framework for understanding the universe, explaining its properties and laws as consequences of its underlying mathematical structure. In a sense, it answers the ultimate question of why is there something rather than nothing, with a disarmingly simple answer: because mathematical existence is inevitable. This idea has a certain aesthetic appeal. It resonates with the human desire to find order and beauty in the universe, to believe that there is a deeper meaning and purpose behind the seemingly random chaos of existence. If the universe is indeed a mathematical structure, then it's a testament to the power and beauty of mathematics itself. It suggests that mathematics is not just a human invention, but a fundamental aspect of reality, a language that speaks to the very heart of existence. The MUH is a bold and challenging idea, and it's important to remember that it remains a hypothesis. While it's supported by the remarkable effectiveness of mathematics in describing the universe, there's no definitive proof. and it continues to be debated and explored by physicists, philosophers, and mathematicians alike. Whether or not the MUH ultimately proves to be true, it serves as a powerful reminder of the deep connection between mathematics and the physical world. It encourages us to look beyond the surface of reality and to consider the possibility that the universe might be even more strange, more wonderful, and more deeply ordered than we ever imagined. The quest to understand the fundamental nature of reality is far from over. The MUH, with its elegant and mind-bending implications, stands as a testament to the power of human curiosity and our relentless pursuit of knowledge about the universe and our place within it.